Hello all. So welcome to this new lecture in this course on time series forecasting with applications in R. Now in today's lecture we'll again revisit some of the functions that we've seen earlier, precisely the one that you see on the slides, which are nothing but the auto-covariance function and the autocorrelation function. Alright. And then probably from last session, if you vaguely remember, we've discussed multiple time series models such as, let's say, autoregressive and then moving average, or even the combination of AR and MA, which is called as ARMA. So probably in today's lecture and the one after this, we'll kind of explore more on this front and then specifically write down some of the important functions of these two time series models, right. So such as autocovariance and then autocorrelation, or for that matter we'll start with the mean function and then variance function and so on and so forth, right. So just a disclaimer that both these sessions will be slightly mathematical in a sense that we'll try to involve slightly different notations, which you'll see on the next slide, of course, and then from there on we'll kind of prove a few things also, right. So it would be a systematic kind of a flow to how do you find a particular autocovariance function or the autocorrelation function of, let's say, some of the basic models such as AR1 or MA1, right, or for that matter let's say ARMA11 and so on and so forth. And then right towards the end we'll bring in the flavor of a random walk also, and then we'll kind of explore a few things about random walk too. Okay. So I think this slide is more of a revision kind of a slide, so we'll kind of revisit the autocorrelation function and the autocovariance function, alright. So before we delve into the autocorrelation function, so probably all of you must have seen the above equation, which is gamma t comma s, right. Now what exactly is gamma t comma s? If you recollect, gamma t comma s is nothing but the covariance between yt and ys, right. So where t and s are particular time points, right? And again, as you remember that this is nothing but the formula for a general covariance. So yt minus its mean, which is mu t, into ys minus its mean, which is mu s, and then you take the expectation of this product, right. And towards the end of this equation, this is the alternative structure of the same equation. So expectation of yt into ys minus the product of the corresponding means, alright. And what exactly is gamma t comma s? Is nothing but the covariance between the time series value at two different time points, which is t and s, okay. And similarly, if you vaguely remember autocorrelation function, so autocorrelation function is nothing but the covariance in the numerator, which is gamma t comma s, and then divided by the corresponding standard deviations, so sigma t into sigma s, okay. So this rho t comma s gives the autocorrelation, while this gamma t comma s gives the autocovariance, okay. Now just for the sake of it, we'll kind of involve slightly different notations and then we'll see how things proceed, okay. So just to be in line with all the notations in probably some textbook and so on and so forth, so we introduce slightly different set of notation. So instead of saying gamma t comma s, what we'll do is we'll define the subscript as the lag between the observations. So here we are using gamma k, right, and then obviously depending on the time point t, so gamma k of t, and this is nothing but the covariance between yt and yt plus k. Alright. So again, if you remember how much is the lag between these two time points, so lag is nothing but k, right. So the subscript we are using here in the autocovariance function is nothing but the lag between the two time series observations, which is k. Now all the other things are kind of exactly similar to the previous slide. So for example, the formula stays the same. So yt minus mu t into yt plus k minus mu t plus k, and then you take the expectation outside, okay. And obviously this is the alternative structure. So expectation of yt into yt plus k minus mu t into mu t plus k, alright. Now again, a small point to note here is that I can either take yt plus k or yt minus k, right, because again if you are only focusing on the lag between the two observations, right. So again the lag between yt minus k and something like yt is still k, right. So rather than writing down covariance between yt and yt plus k, I can actually replace yt plus k by yt minus k, okay. So one can actually look at either sides of yt with a lag of k, alright. So again gamma k gives you what? So gamma k is nothing but the autocovariance between the time series value y at time points t and t plus k, alright. And once you define the autocovariance function, defining autocorrelation function is not difficult at all. So again, notation wise, what do you have? So you have rho k, which is nothing but the correlation between yt and yt plus k, which is as per the formula nothing but gamma k. So gamma k is the covariance divided by the standard deviations. So sigma t into sigma t plus k. Alright. So hopefully if you stick to this notation, probably this set of slides and the next set of slides would be kind of very easy to follow. Alright. So again, just to summarize, rather than writing down gamma t comma s something like that, we are using a slightly different notation, which is nothing but gamma k. And what exactly do you mean by k? So k is nothing but the lag between the observations yt and yt plus k. Alright. Okay, so now we can talk about some very elementary properties of the autocorrelation function, and probably all these are kind of standard properties. So as mentioned earlier, so if you have any stationary process, right? So again, remember what do you mean by stationary process? So let's say you have a constant mean and you have a constant variance, and the autocorrelation function or the autocovariance function should only depend on the lag. Alright. So in that case, what happens is rho k is exactly equal to rho of minus k. And this is again coming from the point that we discussed a short while back. For example, if you write down correlation between something like yt and then yt plus k, this should be obviously equal to the correlation between, let's say, yt and then yt minus k. Alright. So rho k equals rho of minus k, and obviously the second property is kind of a pretty standard property when it comes to any correlation. So the absolute value of rho k should be less than equal to 1. Okay. Or in other words, rho k should lie between minus 1 and 1. Okay. And the third property is kind of interesting. So it's called as a non-uniqueness property. So what do you mean by non-uniqueness property? So let's say if you have a stationary normal process. So stationary normal process means the distribution or the underlying distribution is normal. Okay. And then probably many of you might know already that if you have a normal distribution, so any normal distribution is completely characterized by its first two moments, which are nothing but the mean and the variance. Alright. So similarly here, if you start with any stationary normal process, that process is completely determined by its mean, variance and the autocorrelation function. However, if you have a non-normal process, which is not a normal distributed process, then one can actually find several such non-normal processes with the exact same ACF or the exact same autocorrelation structure, right. So just to summarize this third point, so let's say I can actually bring on the table multiple such non-normal time series processes having the exactly same autocorrelation function, right. So in a way, this autocorrelation function is not unique to a particular normal process or a particular non-normal process. Make sense? So these are some standard properties when it comes to, let's say, defining the autocorrelation structure or where exactly should an autocorrelation lie. So between minus 1 and 1. And finally, non-uniqueness of the autocorrelation function. Okay. Now probably what we will do is we will try to study the ACF function of some of the basic time series models, right. So I think in the last class we kind of discussed white noise, right. So if you vaguely remember what exactly is a white noise, so white noise is nothing but a bunch of random errors, right. So if you want to plot the white noise, it will be nothing but a combination of random fluctuations, alright. So something like that. And obviously the assumptions are that there should be a constant mean and constant variance. So even if you see here, the variance is also kind of constant along the entire timeline, and then you have this constant mean which is mu. Alright. So such a process is called as a white noise process, and on top of that, if you identify or if you kind of put a distribution on this white noise, which is nothing but the normal distribution, then the name is Gaussian white noise. So Gaussian is nothing but normal distribution, right. So Gaussian distribution is a different name for normal distribution. So in a sense, Gaussian white noise means what? So Gaussian white noise is nothing but a standard white noise along with the assumption that the underlying distribution is a normal distribution. Okay. So in a way, if you notice, so we don't have many things on this slide. So this function rho k gives you nothing but the autocorrelation function of this purely random process or a Gaussian white noise process. So if you look carefully here, so rho k is structured as follows. So rho k is exactly equal to 1 if k is 0, right. Now, one point to note here is that if k is 0, what do you mean by that? So, if k is 0, you get something like correlation between yt and yt, right? And all of you know that correlation of any random variable with itself has to be 1 always, okay? So, rho k has to be 1 if k is 0, and for any other lag, so let us say 1 or 2 or 3 or 10, right, correlation should be 0, right. Does this make sense? It should make sense, because again going by the properties of a white noise. So, what exactly are the properties of a white noise? So, white noise, the mean should be constant, white noise should be IID. So, all the observations in a white noise are independent, and hence correlation has to be 0 basically, okay. So, this is a very simplistic looking structure of the ACF of a purely random process or a Gaussian white noise process, okay. Alright, so we will now shift our attention slightly to a sample ACF. So, remember one thing, that obviously in all practical situations the underlying population is unknown, right. So, if you are sitting in any statistics course, or for that matter time series course, etc., then what we assume is that all the population parameters are kind of unknown, and then what we do, we take a sample to kind of estimate all the population parameters, right. So, similarly here, so let us say if you observe this data, so y1, y2 up to yn be the observed time series, right. Now again, so one can actually think of many examples. So, let us say y1, y2, yn would be, or they might be, let us say daily stock prices of Google, or let us say daily temperatures at a location, anything, right. But essentially y1, y2 up to yn are nothing but the observed time series. Then one can actually write down the sample ACF. So, sample ACF at lag 1, right. So, a couple of important points here. So, this is the sample version of the correlation function firstly, and at what lag? So, we are writing down at lag 1, okay. And then this is the formula. So, now again if you see this formula for a second, the formula is not very difficult to digest. So, what we have done is we have kind of replaced all the means by the sample means. For example, y bar here or y bar there, right, or essentially y bar here, right. So, this entire numerator is nothing but the covariance, isn't it, because summation yt minus y bar into yt plus 1 minus y bar. So, numerator is nothing but the covariance, and then denominator is nothing but the variance, right. Because remember one thing, that let us say if you assume that you have a stationary series, so both the means are same, y bar and y bar. So, mean is constant throughout any lag, and we can also assume that the variances are also constant. So, in the denominator, if you take something like under root of variance of yt and variance of yt plus 1, but since both the variances are same, we can actually write down something like that. Make sense? So, this is a classical formula of a sample ACF at lag 1. So, R1 stands for the sample ACF at lag 1, and similarly one can kind of very easily extend this to any other lag. So, let us say sample ACF at lag k would be just a small extension, so Rk, and notice where exactly you see the difference. So, you see the difference probably here, because now we want to find out the sample ACF at lag k directly. So, instead of yt plus 1, we have replaced that by yt plus k essentially, alright. So, the formula becomes summation yt minus y bar into yt plus k minus y bar divided by the overall variance, right. And just to be in line with all the notations used in the textbook and so on, so this could be kind of determined by Ck by C naught. So, this is a kind of a special notation to denote Rk. So, Ck is the numerator by the way, and then C naught is the denominator. So, we have actually discussed two things. So, sample ACF at particular lags, right. So, at lag 1, which is R1, and then sample ACF at lag k, which is nothing but Rk. Okay. Alright, so now we will pay attention to a particular very important plot in time series literature, which is called as Correlogram or the ACF plot, right. So, what exactly do you mean by a Correlogram or ACF plot? So, the idea is kind of very simple. So, if you try to graph Rk against k, so remember what is Rk? So, Rk is nothing but the ACF function or the autocorrelation function at lag k, alright. So, if you try to plot Rk against k, such a graph is called as either a correlogram or the autocorrelation function plot, right. And why exactly is it important? Because any ACF plot plays a very important role in model identification. So just to give you some idea, so let's say how exactly such a plot would look like. So let's say on the x axis you will have k, so k is the lag, right, and then on the y axis you will actually plot the corresponding correlations. So k versus rk, right, and upon looking at the structure of such a plot, which is nothing but the Correlogram or the ACF plot, one can actually identify the underlying time series model easily. Okay. So we will do a small exercise slightly later on this front as to how do you kind of identify the model just by looking at the plot and so on. But the important part in this slide is to understand the idea of a correlogram. Okay. So correlogram is nothing but a simple graph of k versus rk. Right. Okay. So now the other side of the coin is a slightly different autocorrelation function, and probably I am kind of introducing this idea for the very first time. And the name of such an autocorrelation function is called as partial autocorrelation, or PACF, alright. So partial autocorrelation function. Now again the idea is kind of easy if you follow this twice or thrice, right. But what exactly is PACF? So let's say PACF of any order k, let's say alpha k, so alpha k denotes the PACF, is nothing but the partial correlation coefficient between yt and yt minus k, right. So this is nothing but kind of the correlation between yt and yt minus k. But you have something extra here. So conditional on the intermediate values of the process. So what do you mean by that? So let's say this kind of a conditional correlation. So how do you write down conditional probability or conditional correlation? By a vertical line, something like that, right. So again if you read this statement, so correlation between two variables, so yt and yt minus k, conditioned on all the intermediate values. So what exactly are the intermediate values, or what values fall between these two? So which are nothing but let's say yt minus 1, then yt minus 2, etc. up to yt minus k plus 1, something like that, right. So this formula is nothing but the formula for the PACF, or the partial autocorrelation function. Okay. Or in other words, this PACF or alpha k is nothing but the autocorrelation between yt and yt minus k, removing their linear dependence on the intermediate values, which are nothing but yt minus 1, yt minus 2, yt minus 3, and so on and so forth up to yt minus k plus 1. Okay. So even if you understand the simple idea that in practice we have two very important autocorrelation functions. So one is the ACF function and the other one is the PACF function, right. And for that matter, one actually has plots for both these. So one can actually construct plots for both ACF function and the PACF function, and collectively these two plots kind of are very important in model identification. So if you want to find out that your practical data should follow what kind of a model, so the very first thing that researchers do is kind of plot these two plots, which are nothing but the ACF plot and the PACF plot, and then using the structure of these two plots, then they are kind of able to identify the underlying model. Okay. All right. Now what we will do is we will kind of expand on some of the elementary time series processes, and then we will try to find out the ACF functions for those. Okay. So now the first one is the autoregressive process. So probably all of you know the structure. Now again, just for revision, I have written down the structure again here. So if you recall, the general structure of an autoregressive process of order p is nothing but something like that. So yt is kind of regressed on its historical data. So yt minus 1, yt minus 2 up to yt minus p, and then eventually you have a error term which is et. Alright. And how exactly do you identify the order? So the number of historical terms of y that you take determines the order. So for example, here if you are taking p such historical terms, then the order becomes p. Okay. So this is a general structure of the ARP process, and some properties about all the parameters are as follows. So ET is nothing but IID sequence with mean 0 and a fixed variance which is sigma square E, and all these are the model parameters. So phi 1, phi 2, phi 3 up to phi p, and then C, and then sigma square E. Alright. So I think this slide just gives you a revision of a general autoregressive process of order p. Okay. Now further, if you further assume this thing, that all the means or the mean throughout is a constant which is mu. So expectation of yt is the same as expectation of yt minus 1 is the same as expectation of yt minus 2 and so on and so forth up to expectation of yt minus p, which is nothing but some constant mean which is mu. Okay. So, the first line just tells you that you are kind of assuming that you have a constant mean throughout. Okay. So, now can somebody tell me that what would happen if you take expectations on both sides of this model ARP? So, again if you go back for a second, this is what you have, right. So, looking at this structure here, if I take expectations on both sides, so what would you have? So, expectation of yt is nothing but c, so c is a constant, right, and then plus phi 1 expectation of yt minus 1, right. So, if you follow, and then dot 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 plus the last term is phi p and then expectation of yt minus p, and now the last term would be 0 because expectation of the error is 0. Hopefully, this should be clear now. Alright. So, if you take expectation on both sides, this is exactly what we get. Now, as per our assumption that all the means should be constant. So, what do you have? So, this is nothing but mu equals c plus phi 1 into mu plus phi 2 into mu up to phi p into mu. Alright. So, I am basically replacing all the expectations by mu because we are assuming that the mean is constant. Right. Now, can't you solve this equation for mu and then get a formula? So, of course, we can, right, and this is exactly what is given in the next slide. So, if you take expectations on both sides, this is the first step, and then bringing all the mu's on one side, this is nothing but the value of that expectation. So, c divided by 1 minus phi 1 minus phi 2 minus phi 3 dot 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 minus phi p. Okay. So, again just to summarize, if you assume a constant mean throughout, this is nothing but the value of that mean. Alright. Now, what we will do is we will kind of consider some very basic processes. So, let us say AR1. Okay. So, what do you mean by AR1? So, AR1 means the order is 1. So, you are kind of regressing the current value on just one past value, which is yt minus 1. Okay. So, this is the structure of AR1. So, yt equals some constant c plus phi 1 into yt minus 1 plus the error term. Okay. Now, a very interesting property of an AR1 process is as follows. So, thus given yt minus 1, yt actually becomes independent of all the previous values, isn't it? Because since this equation does not contain any of the previous values, and then given the fact that let us say yt minus 1 is a constant, right. So, given yt minus 1 means what? So, given yt minus 1 means that one can actually assume that this yt minus 1 is kind of a constant or it behaves as a constant. Okay. So, assuming that yt minus 1 behaves like a constant, yt becomes independent of all the previous values, right. So, yt minus 2, yt minus 3, etc. And such a property is called as Markovian property. Okay. And hence, this AR1 process is in fact a Markov process, right. So, just to summarize what exactly you mean by Markov process. So, Markov process means if the current value is only dependent on one past value. So, for example here, so since yt only depends on yt minus 1, obviously given the fact that yt minus 1 acts as a constant, so an AR1 process can be thought of as a Markov process. Okay. Now, again finding the mean is not difficult. So, probably you can pause the video if you want and then try finding the mean of this AR1 process. So, one easy way to do it is if you go back, this is the general mean for ARP, right. So, this is the general mean for ARP. So, simply if you replace P to be 1 here, you will get the mean of an AR1 process, right, okay. And which is exactly what you see on the next slide. So, the mean of the AR1 process happens to be mu, which is C divided by 1 minus phi 1. Okay. Alright. So, now further, so what we can assume is we can still assume that since we are assuming all the means to be constant, so why not just put some constant value which is 0 for a trivial purpose, alright. So, assuming that C equals 0, which implies mu to be 0, so the constant mean in fact is nothing but 0, and we are putting one more assumption here that the process is in fact variance stationary. So, what do you mean by variance stationary? So, variance stationary means that all the variances should be also the same and constant, right. So, for example, gamma 0 is a notation for variance, right. So, probably we have seen this notation in the earlier lectures. So, gamma 0 is nothing but variance of yt equals variance of yt minus 1 equals variance of yt minus 2 and so on up to the last term, and we are also assuming that all the variances are same and equal to this guy, which is sigma square y. Now obviously sigma square y does not depend on t, so variance in fact does not depend on t, and all the variances at any lags are equal. Okay. So if you now combine these two assumptions, that the overall mean is 0 and all the variances are equal and equal to sigma square y, so can you essentially find out the variance of the AR1 process. Okay. Now again going back, so this is the AR1 process structure which is given here, right. So if you kind of write down variances on both sides now, so rather than expectation, if you write down variances on both sides, then what will you have? Okay. And this is kind of explained on the next slide. So sigma square y would be nothing but the expectation of the AR1 structure. So this is nothing but the AR1 structure and the square of that. Because remember one thing, that variance of yt is nothing but expectation of yt square minus expectation of yt whole square, isn't it? So this is a standard formula for variance. So variance of any random variable is nothing but expectation of that random variable square minus the whole square of the expectation of the random variable. Alright. So using this structure we have something like that. So variance of yt equals e of yt square minus e of yt whole square. Now since we are assuming that the expectation is 0, so this part goes away by the way, and we are only left with variance of yt being expectation of yt square, which you see here. Alright. So sigma square y is nothing but expectation of phi 1 yt minus 1 plus et whole square, and now I can actually expand this. So if you open the brackets, what will you have? So you will have something like phi 1 square and then expectation of yt minus 1 square plus expectation of et square plus the cross product term, which is 2 into phi 1 into expectation of yt minus 1 into et. Now the most important question is, why is this cross product term equal to 0, right? So if you visualize this for a second, what we have is, so phi 1 is a constant firstly, right. So phi 1 comes out of the expectation, and then inside the expectation you have yt minus 1 into et, alright. Now again if you go back for a second and look at this general AR1 process, so what exactly would be yt minus 1? So yt minus 1 would be nothing but similarly c plus phi 1 yt minus 2 plus et minus 1 and so on. So similarly I can write down yt minus 2, yt minus 3, yt minus 4, etc. Now if you see this yt minus 1 structure, yt minus 1 does not depend on et, right. It only depends on et minus 1 and the further lags. So et minus 1, et minus 2, et minus 3, etc., but not on et, right. So I can write down a small assumption here on the next slide, that yt minus 1 is kind of independent of et. So yt minus 1 is independent of et, and hence the expectation has to be 0, right. So since yt minus 1 and et are independent, the expectation of their product has to be 0, okay. And then so this entire cross product term becomes 0, right. And then so this boils down to phi 1 square, and then expectation of yt minus square is nothing but the variance as per this assumption, okay. So if you remember, we are assuming constant variances, right, and then plus expectation of et square would be nothing but the variance, because expectation of et is 0 again. So finally it boils down to this, alright. And then if you combine the LHS, so LHS is sigma square y, RHS is this. So now I can actually solve for the variance, isn't it? So this implies that my sigma square y would be nothing but sigma square e divided by 1 minus phi 1 square, okay. So essentially the variance of any AR1 process, assuming these two properties hold true, is nothing but given by that formula. So sigma square e divided by 1 minus phi 1 square. Okay. So probably now what we'll do is we'll kind of explore more on couple of other properties of AR1 and then slowly transition into the moving average process, right. So we'll kind of deal with these two sides of the coin, so autoregressive and then moving average, and then what we're trying to essentially do is kind of simplify a few properties of both these processes. For example, let's say autocovariance, then autocorrelation, and then of course under some assumptions. So if you assume, let's say, stationarity, so stationarity means constant mean, or constant variance, then I think we will kind of extend this to the next lecture also. Alright. Thank you.